Good evening, everyone. My name is Barry McMullen. I'm the chair of the Energy, Environment, Climate Action Division of Engineers Ireland, and it's my pleasure to welcome you all, professional engineers, members of the general public, anybody who may be interested in the event. You're all very welcome to this webinar event. It will be recorded, so there will be a recording available afterwards as well, just to be aware of that. It's my pleasure and privilege to welcome this evening Dr. Hannah Daly of UCC, the Environmental Research Institute and the MaREI Centre based in UCC. Hannah her title this evening is Pathways to Zero, How the Energy System Can Rise to the Climate Mitigation Challenge. But it's a very timely topic. Hannah herself is a lecturer in Sustainable Energy Systems Modelling at UCC. She leads now the development of the Times Ireland Energy System Model, which, work on that has been going on, very advanced work on that has been going on for at least 10 years now in UCC. Hannah's previously worked at the International Energy Agency as a modeler for the World Energy Outlook team. Many of you will be familiar with the IEA World Energy Outlook, sort of the gold standard in energy forecasts on a global basis. And her work there focused on the interaction with the UN Sustainable Development Goals. So Hannah has also recently served as a member of the Carbon Budgeting Committee for the Irish Climate Change Advisory Council. So a committee of the council was set up, as many of you will be aware, under the 2021 Climate Action Act. The council has an expanded brief, and last week just published its recommendations for Ireland's first national carbon budget programme, or greenhouse gas budget programme. So Hannah has been involved in supporting the council in that work, particularly from the energy system modelling point of view. So as I say, it's my pleasure and delight to welcome Hannah this evening. I'm going to hand over to her in 1 second, but just to say for everybody, you should have access to a Q&A facility. So if you want to post questions while Hannah's speaking, we'll collect the questions. We'll let Hannah go through her full presentation first, but you can post questions at any stage, and then we will allow plenty of time for questions as well. So you can do that as things are going along. So with that, I'll just hand over to Hannah. Thank you very much.
Thank you very much, Barry, and thanks everyone for giving me your evening, welcoming me into your house, and I welcome you into my house. You might hear some of the evening activities, which includes my kids going to bed behind me in a while, so apologies if that's disruptive. But thank you all for coming, and as Barry said, here tonight I'm going to give you an oversight of the process that I've been participating in, which has led to, I suppose, contributed to the Climate Change Advisory Council setting forth its first set of carbon budget recommendations. So we've been with a, let me get my slides off the go. There we go. Go first slide. So this is very much a collaborative effort. Before I jump into the presentation, so with a team of researchers, PhDs, and wider support from across the Energy Policy and Modelling Group at UCC, at the MaREI Centre and at the Environmental Research Institute, we have undertaken the redevelopment of the Irish Times model and developed a new model called the Times Ireland model, which is, I suppose, fit for, and we call it TIM. It's fit for answering these new, much greater ambition in energy systems decarbonisation, and takes into account new developments in the energy modelling landscape, new developments in energy technologies and fuels, and of course the climate policy and kind of social imperative of steep decarbonisation. So this is a first assessment, I think, that's been published tomorrow. I think the Climate Action Plan 2021 will be published, so that will be the second published assessment of energy systems pathways, which meet these very deep 2030 decarbonisation targets with the Times Ireland model. And TIM can be used as a tool for decision making and planning. It's a tool, not an answer. It explores different futures for sectoral decarbonisation ambitions, looking at the technology investments, energy demands and fuels trade-offs and linkages and complementarities across sectors. So this analysis, as I said, was developed to support the Climate Council's consideration of the implications of carbon budgets in the coming decade. I in no way speak for the Climate Council or indeed the Carbon Budget Committee. I'm not a member of the council itself, but of a subcommittee or of a committee asked by the council to advise on certain topics. But you'll see if you read the technical report underlying the CCAC's carbon budget recommendations that were published recently, this type of work underlies an awful lot of the insights in that related to energy systems in that report. So we're very pleased to be able to engage with them while we were developing the model with them and other stakeholders to be able to, I suppose, answer the questions that we need to. One of the major insights that you'll get from this presentation is that there's a very, very short time horizon to 2030. It's nearly 8 years away. And that requires a faster energy transition than has ever been achieved, faster than the natural renewal time of many technologies. You know, cars last for 15 years, large power plants last many decades. And this has wide-ranging implications. So we have to look at a whole different set of solutions than previous efforts. And one of the key insights is that abatement with new fuels and technologies alone, while they will be extremely important, new technologies, new fuels, and changing the physical system, resilient pathways to decarbonisation requires a structural change in energy demands. I'll go through what that means later. So first of all, the Times Ireland model, TIM. It's the type of model is known as an energy systems optimization model, an ESOM. And that calculates what we call the least cost configuration of the energy system, which meets future energy demands respecting technical, environmental, social, and policy constraints defined by the user. I've started to put least cost in very heavy inverted commas because it was the speed of transition and the target that we're facing to 2030. The results are far more dominated by how quickly we assume things can change rather than the cost of things. Maybe I'll go through what that means a little bit later. But what the model does is, given the landscape of the energy system, how different supply sectors link to energy transformation, electricity sector, potential hydrogen, bioenergy, and how those all link to the end use sectors, the sectors that actually provide us the services that we need for energy to transport us around, to light and heat our homes, to make products, and so on. So we describe the base year, and the base year is 2018, how the energy infrastructure looks, how things are tied together, what the cost of running different technologies is, what fuels cost. We look to the future, we give it final energy demands out to 2050 or even indeed 2070, what passenger kilometers will look like, how many homes will need to be heated, what industry looks like. We can give the model different CO2 constraints on the energy system. And just to be clear, this is just the energy system. So we can give a whole carbon budget, so cumulative constraint on energy, or we can give it an annual target, for example, 51% by 2030. We can give it technologies, fuel costs, and efficiencies out to the future. So we take a range of best estimates about what electric cars will cost in the future, what hydrogen production will cost, both the existing and future cost and performance of those technologies, what the resource availability is, and very important, a set of user-defined constraints. So those can represent, for example, what we think the speed of technology uptake is, what policies are in the future, how those sort of real-world social barriers or policy barriers will kind of define how quickly things can change. And we put it in as a least cost optimization model, and it calculates what the energy system, what an energy system is, which can meet all of those constraints, respecting the user constraints, providing the final energy demands, and respecting, for example, resource availability constraints. It tells us what the investment and operation cost of energy technologies is in the time horizon, what emissions trajectories per sector, which fuels are imported, which are extracted, the imports and exports, marginal energy prices. So this is a framework in what's known as the Times framework. It's used in many different countries. I worked on the at UCL when I was a postdoc, the UK Times model, which also informs the UK's carbon climate committee. And it's used in both academic and policy settings to look at integrated pathways to meeting energy targets. So we've submitted the documentation paper for the model for peer review. We underwent extensive stakeholder engagement in March. Maybe some of you in the audience participated in that, and thank you if you did, to look to kind of throw open the model and to examine the assumptions and the constraints that we apply. And we're trying to make this process as open as possible. And this is just a slide I like to use I suppose, to understand why model. What's the use of a model? If we know we need to get to zero and we need to get there as quickly as possible, why do we need this kind of integrated model that can tell us things? And oftentimes it tells us things that we already know. I like to see models not like horoscopes or crystal ball gazing or even to provide a single solution. I like to see models like maps. So models are like maps in that they don't prescribe a single solution. They give one solution per scenario, and they don't even tell you what destination you're getting to. If we were all together here going to set off on an expedition to Carrantoul, to climb Carrantoul, we wouldn't go there without a map, because you need a map to gather the best knowledge about the route. You need to understand the trade-offs of going one way versus another way. It also facilitates discussion in an evidence-based way. So we gather all of our evidence and we can have a shared, meaningful, consistent narrative about where we want to go. And that's what this model does, because achieving net zero greenhouse gas energy systems requires every sector to go as low as possible. And these system models, while they don't have as much granular detail as a lot of the kind of sectoral models, so there's power systems models or car stock models or residential models of a factory or a house, which understand decarbonisation of individual units. These optimization models give a big picture approach about how everything fits together to make sure that we don't have any blind spots, that we're considering the best use of different availabilities, respecting national constraints, preventing blind spots. Give the example, if we have a limited amount of sustainable bioenergy that we can produce in the country, where should we use that? Should we use that to create biofuel, to put in petrol and diesel cars? Or is it better to electrify those cars and to use the biofuel in hard to abate sectors? So this is what the models are very good at looking at in different scenarios. So jumping on to Ireland's challenge, I'm sure you're all aware of now, and the huge amount of coverage that climate change is getting, that Ireland has one of the most ambitious targets for decarbonisation in the world. And I'm not sure if you can see my pointer there, but this is what I've ranked the different countries that I've seen decarbonisation targets of in terms of ambition relative to between 2018 and 2030. So the red there is 2018. So Denmark is, I think, the world's leading in terms of its ambition to decarbonize its whole economy. So this is our whole economy targets, 63% and actually 70% relative to 1990. So Denmark is really leading ahead, and I think we can learn an awful lot about Denmark and how they're going about this. In Ireland, our ambition relative to 1990 is only 44%. That's because we've had relatively little progress since then. Our our emissions in the year 2000 were the same as they were in 1990. But relative to 2018, we have a target of nearly halving emissions. Now, Germany, 49%, the US, 47%, and so on. And Ireland's target relative is kind of compounded because we have a very high share of emissions from agriculture, which make this target even more challenging when agriculture is not going to abate as quickly as this. So to give, I suppose, a picture of where we are in 2019, the energy system, and by energy, I mean electricity, transport, and heat, accounted for 34 million tonnes of carbon dioxide equivalent. Agriculture accounted for 21 million tonnes, and other, that's mainly process emissions and waste, accounted for 5 million tonnes. Those are the standard emissions that you'll see in the EPA's emissions account. Our energy sector emissions are broadly split into transport and heat being the main sources of emissions because they're very much fueled by fossil fuels, and then electricity. The emissions intensity of electricity has fallen very rapidly and actually has offset a lot of the increase from transport and heat. Add to that aviation, which isn't included in our national targets at the moment. Maybe they will post 2030, but that's another 3 million tonnes international aviation, which we don't account for in our targets. We have a certain amount of land removals, about 6 million tonnes in 2019. That number is uncertain, that's why it's a little bit faded. And we also have a large source of emissions in land from degraded bogs. So this is the picture of 2019. And the goal is to reduce these by 51% between 2018 and 2030, and then to get to net zero by 2050, where any remaining emissions are balanced by sinks. So what we need to do is to reduce the sources as quickly as possible and to increase the sink. Now there's a whole other presentation on, you know, agriculture, land source and land sink, but so that, like this presentation will really focus on the blue bit there, because this will be required to get as low carbon as quickly as possible to meet the target. And if we look at the sort of historical picture of our greenhouse gas emissions, and this is not including land use, by the way, because we're only starting to really consider land use, given that it's just been included in the targets. So in fact, our 2020 emissions were almost the exact same as they were in 1990, and there's quite a similar split between energy and agriculture as well. So we're only back to where we were in 1990. During the COVID-19 pandemic, emissions fell last year by 3.6%. And that was a combination of factors. That was our transport emissions fell very rapidly as we stayed at home, but that was offset by a lot of increase in residential energy demand. Fuel prices were very cheap, and we stayed at home, so residential emissions rose a lot. But our emissions last year only fell actually at a slower pace than they did the previous year, and they fell at a slower pace than they will have to meet the first two carbon budgets. So this gives a picture of what the Climate Council announced this week. So our first carbon budget period will be required to fall by 4.8% per year, giving a total carbon budget that is the cumulative greenhouse gas emissions between 2021 and 2025 is 295 million tonnes of CO2 equivalent. And the second carbon budget will require 8.3% per annum fall. And that will get us to half of 2018. Now these numbers here represent numbers including land use emissions. So the numbers don't quite add up because this green line here doesn't include land use emissions. And then, of course, the title of this talk is Pathways to Net Zero. And I'm going to focus on the pathway, I suppose, as opposed to the destination, even though the modelling results do give us an indication. And I think one of the brilliant things about the new Climate Act has been to have a definite target for 2030, because, you know, I think most people who are in any kind of decision-making capacity will be retired by 2050. Maybe a lot of them will be even retired by 2030, but at least they'll still be alive in 2030. And sorry if that's offensive, but I think the generational sort of view here is important. You know, the target for 2030 is so stark and so immediate that we have to take action immediately. When we're just looking out to 2050, it's tomorrow's problem. But now I think that the attention has really changed, and the focus will shift as well. Let's look at how this potentially this last target, so this 2030 target, can be met. So the Climate Action Plan 2019 was a plan to reach our previous targets. So that was agriculture emissions were to fall by 12%, and the rest of the system, energy process and waste emissions, were to fall by 28% to reach our overall ambition for 2030, according to the EU 2030 package. So this is the 2019 Climate Action Plan, which required, 900,000 EVs, 500,000 retrofits, 70% of renewables with electricity. So these headline numbers for the 28% are already debated about whether they're too ambitious. Now, to meet the overall 51% reduction target within the same 10-year carbon budget period, we have a number of options. Either agriculture and energy can both fall at 51%. And if anyone's been following the news, you'll see that that's likely not going to be the case when the Climate Action Plan tomorrow is announced. If agriculture takes a 40% reduction, the energy system will need to reduce by 57%. If agriculture falls by 33%, energy will have to fall by 61%. and so on and so forth. So the current agri-food strategy was to target a 19% reduction in greenhouse gas emissions. This is what analysis from Teagasc says is the maximum that can be done with technologies that exist without affecting food production, the level of food production growth that is projected. That would require the energy system to fall by 69%. So we model what each of these different targets means for the energy system. And the answer is that it gets progressively more and more challenging. And it means that the agriculture share of greenhouse gas emissions starts to dominate the energy system. And indeed, by 2050, it's likely that agriculture will be 100% of our emissions. This is a slide which is useful to benchmark these different pathways against the global what's required globally. Now, the global IPCC special report on meeting 1.5 degrees, these are modeled pathways in grey, which meet this Paris Agreement goal of limiting global warming to no more than 1.5 degrees above pre-industrial levels. So, so these grey pathways, this on the left is for methane from agriculture, and on the right is for CO2 from fossil fuels. And you'll see that the benchmark is from 2010, and the sort of the benchmarking against Ireland really depends on which base year you're starting at. Methane emissions have risen very substantially since 2010, since the removal of the milk quotas. And these different pathways here, many of them don't land kind of within this IPCC range. And I'm not saying that this, that the global range is prescriptive to countries. It's just useful to benchmark where Ireland would be against the global. And then this grey range here is for CO2, which is approximately halving of emissions. Now, it's important that basically to get to 51%, you need to choose one color. So you can go, purple, which is kind of light on agriculture and very steep on energy, or you can go red, which is very steep on agriculture and very light on not very light, but less light, but less heavy on energy. So that's just to kind of to look at the trade-offs between agriculture and energy. And before jumping into the model results and telling you a bit about the different changes that are needed across the different sectors, you probably can't click on that link on the screen, but you can quickly write it down, I suppose, or someone can pop it into the chat. This is the first time we're kind of publicly releasing this website, which we have been using to do stakeholder engagement, to do results diagnostics, and now to sort of disseminate results about what different scenarios mean for the energy system. So you can go in and you can click and compare two scenarios against each other for a range of different scenarios that we've done here for each of the different sectors. And I hope that's useful. It's sort of a first iteration. It takes a bit of getting used to, but I hope it's useful for maybe more technical people who want to dive into the results. So the first headline results I want to show you are the marginal abatement cost. So we're giving here the average marginal abatement cost between 2025 and 2030 in the core mitigation scenarios and different scenario variants. So for those of you who don't know, the marginal abatement cost represents the cost of removing the most expensive ton of CO2 in each scenario from the energy sector. So it's sort of what is the cost to the energy system of removing that one last ton of CO2. So it's a reflection of the sort of the peak in effort rather than the average effort, and we'll give costs later on. So just to benchmark the previous, if we model the previous Climate Action Plan 2019 goal, the 28%, the marginal abatement cost is around €200 a ton. And these different scenarios here where energy falls by 51, 57, 61 and 65 show that the effort gets progressively steeper and more difficult the harder it gets. So this is the core set of scenarios where we have business as usual energy demands. So we continue to drive as much, we grow our car travel, our houses continue to get bigger. And we continue to use cement and other products at the same rate. We don't assume any bioenergy imports, so we assume we can't meet these targets with additional bioenergy imports. We assume that there's 4 times the level of 2018 indigenous bioenergy production. No CCS, carbon capture and storage, available for the power sector before 2030. We do assume some CCS for cement production because that's the most. I suppose this was the solution that we saw for there. No hydrogen import, and up to 18 gigawatts of variable renewables of wind wind and solar, which, you know, we want to be both conservative, but this is really what it takes to solve. So I suppose one of the main insights is that there's a solution and that is good, so that there are solutions, but they get progressively more expensive as you go up the line. Now, I mean, the future is not written. Technologies aren't fixed, demands aren't fixed. There are, you know, changes. So we do look at alternative scenarios. And the first very interesting scenario that I'm a big fan of is called the low energy demand scenario. And this has been developed by my PhD student, Ankita Gower, who is looking at basically, she modeled the core energy demands kind of on the basis of population growth, incomes, and so on. She looked about what if we could decouple energy service demands from growth as we have, you know, with this growth as we have in the past. So what if car travel stabilizes and reduces? What if freight transport stabilizes? What if we use less carbon intensive materials, lower heating, you know, wearing woolly jumpers, like myself and Barry are this evening, to lower heating demands? And it shows you here that the effort comes down hugely substantially, but still very, very difficult to get to the 65% level there in 2030, a marginal abatement cost of €700 a tonne. We also modeled what's called what I'm calling a tech optimism case. So we basically relax a lot of these technology constraints here. So we have up to 25 gigawatts of variable renewables. We're allowed to import some hydrogen, although that doesn't really come in until after 2030. We import more bioenergy, and we have some 400 megawatts of CCS of both gas and bioenergy CCS available from 2027, allowing some growth. And again, here, this reduces the marginal abatement cost substantially. And then we have another scenario where we stack the low energy demand on top of tech optimism. And there it starts to look really achievable, you know. So I suppose, I mean, this is really the main insight, that you've got difficult choices here. You know, if some technology pathways don't work, you know, the whole target will become very infeasible. You know, if the offshore wind industry doesn't take off, if we can't use bioenergy. We looked, for example, at what if we couldn't increase any indigenous bioenergy, and the model simply wouldn't solve. There were no pathways to get there. Now I'm just going to take a dive into the sort of the primary energy demands and so on, before looking into the sectors. So in 2018 now, and still now, fossil fuels are by far the main source of energy that we use to fuel our societies and fuel our lives, despite, you know, decades of knowing about climate change. So 90% of our energy demand, primary energy demand, comes from fossil fuels. Oil there in red is the main source, which is completely drives our transport sector and a lot of our heating as well. Natural gas there, which goes into our residential sector, industry, buildings, other buildings, and power generation. We still have a substantial amount of solid fuel on the system, so oil, gas, peat, and coal. And then 6% of our primary energy comes from wind, solar, and hydro from primary renewables, and 3% comes from bioenergy. So that needs to flip completely by 2030. So, you know, depending on here, 51% target, you know, well, the first insight is that coal and peat are removed completely from the system. So there's no space for any coal or peat, not to mind, you know, low emissions coal, no peat, no open fires. By 2030, and oil and gas, oil falls very substantially as well. So when you get to 65%, oil goes down to 14% of our primary energy. Gas is fairly resilient. It's the least carbon intensive fossil fuel, and it's required, I suppose, to balance out variable renewables in the electricity sector. But really, the next decade is the decade for other renewables, wind and solar, ambient heat as well, to heat our homes, and as much bioenergy as we can produce sustainably. Going into the final energy consumption and power generation from different sectors, over here on the left is power generation by fuel source. Now we have, you know, a good amount of wind, but still oil and coal on the system. That needs to, we need to both dramatically increase power generation, so nearly a doubling of power generation in the most ambitious case, in the 65% case. And it maximizes the potential for wind and solar. Industry, then I think I would like to look in more detail at pathways for the industry sector. The model is still kind of being built, and I think the industry and services sectors are sectors that we want to look at in more detail, because as you can see, there isn't a huge amount of change in these sectors, more bioenergy and more electricity. Transport there progressively more, currently very, very oil dominated. Half of our car sales are still SUVs, 3 times as many cars on the road as there were in 1990. Ours is a car dominated society, and that needs to flip completely as well. So again, electrification there, electricity fuels an awful lot of cars by 2030, bioenergy, which comes from indigenous sources. So, and the model actually likes natural gas and compressed natural gas as well as bio CNG, which it would be interesting to talk about as well. Buildings then there is a complete removal of coal and peat, and very, very strong reductions in oil. Now, my house is heated by oil, and this is, I suppose, I think really one of the most challenging pathways for decarbonisation. So how to get our houses off oil and onto ambient heat there in blue, and other renewables, and massive electrification of heating. This is the broad sort of set of technology solutions and energy pathways to meet the 2030 target. These slides are basically clippings from the website, and you can play around with different scenarios yourself. But what I'm taking here is there's a typo there, but this is on the left, the 51% scenario, and on the right there's the 65% with tech optimism scenario, just to show you the kind of range of different scenarios that we get when we model these things. So all the core scenarios without low energy demands or variance in the technologies, they grow renewables capacity to the maximum level in 2030, and we get to 73% renewable electricity generation. That requires alone a quadrupling of renewables capacity by 2030. So 7 gigawatts of offshore and onshore wind, and already as much as possible by 2025, 2 gigawatts of offshore wind by 2025, although given recent developments, maybe that's not feasible, and then 3 gigawatts of solar in 2030. So the speed at which we can roll out this low carbon electricity is the bottleneck for decarbonising the rest of the system. If we can't get to this level, it makes decarbonising the end use sectors much, much more challenging. If we have the tech optimism case here, where we can do more wind, more solar, some hydrogen import, early CCS deployment, it enables further power system decarbonisation. So that is basically an option to make these things easier. What is driving power generation? No surprise, data centers are on the news. So a lot of this growth in this 65% is driven by data centers. And here we take the EirGrid kind of the central case from EirGrid projections for electricity demand from data centers. And transport demand there only becomes very significant in the E65% case, where we have more than 1 million EVs, vans as well, and freight vehicles on the roads. So basically, the key insight from here is that the growth in electricity demand is a key kind of problem. Just because something is being electrified doesn't mean that it makes the whole system easier to achieve. We need to push efficiency and demand management as much as possible, and to reduce demands. So we're doing a policy brief now. A master's student is looking at different variations in data center demand. It makes decarbonisation a lot more feasible if you assume that there's maximum amount of renewables that we can get on the system by 2030. So now just looking at the transport sector, there'll be no surprises here that the steeper the decarbonisation objective, the more electrification and the more biofuels. We actually get quite a bit of bio-CNG in the more ambitious scenario here on the right, the 65% scenario for freight. Whether we're taking into account the sort of barriers to compress biogas and the charging infrastructure costs, not clear yet, but it is one pathway potentially. So we want to maximize the electrification of cars and vans, not just cars, but vans too. Additional biofuel blending, again, from sustainable sources of biofuel where possible. the number of EVs that this is like one of these sort of big headline numbers that people discuss, you know, is 900,000 EVs enough, or is it too much, or is it possible? So depending on the scenario, the optimal number is anything from 600,000 to 1.6 million passenger EVs. Obviously that 1.6 million passenger EVs by 2030, that requires almost all sales from now on to be electrified. And, you know, even though we're doubling the number of EV sales every year, we won't get there that quickly. Or it will retire massive scrappage schemes in 2028, 29, where we're taking the SUVs that we're buying this year off the road and we're paying people to do that. So that's something that we have to think about right now. And no plug-in hybrid sales, except to a certain extent for vans. Plug-in hybrids are a transition fuel of, you know, of the past decade. There's no space for plug-in hybrids, or indeed hybrids. If someone is considering buying a plug-in hybrid, they're probably better off wait a year or two and buy a full battery electric vehicle when the charging infrastructure is better. And even now that the ranges are fantastic. So I would say that it's a good time that the government has taken away the subsidy for plug-in hybrids. The residential sector already went through a lot of this, but basically complete removal of coal and peat, up to 600,000 retrofits between now and 2030. And this is one of these key barriers as well, because retrofits are a requirement to install heat pumps. So heat pumps are not suitable for or pure electric heat pumps. Hybrid heat pumps might be a solution, and that's something that we're looking into as well. Very large scale reduction in kerosene heating, and as I said, that's probably one of the biggest challenges that we'll face. Large scale electrification and district heating where possible in apartments, and this is another kind of research avenue that we're going down, whether we can use waste heat from data centers for apartments and urban areas. What will it cost? This is, of course, a huge amount of interest, and made some of the news and headlines that was released on the back of the Climate Change Advisory Council's report. And those numbers come from this model. So the overall cost of an energy system with no mitigation at all is on average about 12.5 billion euros a year. That's the cars, the boilers, you know, the power plants that just supply our energy system. Now, the previous level of ambition, the 28% reduction, would increase that by about 500 million a year to 13 billion. There's lots of caveats down here I'll let you read, so you know it's not as simple as what the cost is. The lowest level of ambition for the energy sector, a 51% target, would increase that by another billion a year. And then the 65% requires a huge change in transport, and that is kind of represented by that scrappage of old cars by another 2 billion a year. So depending on what you're measuring, it costs between 1% and 3% of modified gross national income. So that's the sort of realistic measurement of what our national economy produces a year. And that is above the previous level of ambition. So that is an awful lot of investment. These are annualized costs, and if you just looked at the upfront investment in the next decade, the number would be a lot higher, because basically we annualize the cost over the lifetime of different investments. So for example, if you buy an EV in 2029, a lot of the annualized cost would be after 2030. So we're not capturing the kind of the investment that needs to happen in the next decade. This is kind of spread over the lifetime of technologies. But we have to see an awful lot of this investment in terms of not a cost, but as an investment. So this brings very long-term savings and benefits. It reduces costs in the 2030s and 2040s. It offsets, the green there is a reduction in fossil fuel imports. So we import 5 billion euros a year of fossil fuels. Instead of spending that money on fossil fuels, we could be spending it on indigenous infrastructure, renewable low carbon infrastructure, which brings good quality jobs, improves the value of our homes, makes our homes warmer, healthier, cleaner, huge fossil fuel savings and economic growth. But it's crucial that industry can capture parts of these value chains. If we're simply importing bioenergy to replace imported oil, then we'll lose an awful lot of these benefits. So the key is for the economy to capture parts of this low carbon value chain to drive the support and economic growth for this transition, because industry and people will support this if they can see the benefits through economic growth. It's not, I was disappointed a little bit with the rhetoric from Taoiseach Micheál Martin at COP. He said, we have to do this, you know, we've been so bad and we have to, you know, it was very sort of like, look, we've been bad and we have to get along with this. The benefits of this could be huge if we frame this right and we get it right and we do it now. If we're just kind of seeing this as a kind of a stick to punish ourselves, then we won't be bringing society along. Just a few more slides. I'd like to have a good time for questions. And the last thing I want to talk about is a little bit more in depth about the low energy demand scenario, because I think it's really important. It enables a less rapid energy transition, and it can bring many multiple benefits. So I didn't give any results for the low energy demand scenario there, but if you're interested, you can click through the website by yourself. What it requires is large scale mobility in investment in sustainable transport, better planning to allow us to live in more dense settlement patterns, no more one-off housing, for example, and public engagement to shift practices towards lower consumption. So, you know, that we're looking at sufficiency rather than maximizing our consumption, and that we're aware of the impact of our energy demands. In the transport sector, for example, this is a what if scenario. So we looked at what if private cars had, instead of a 73% share of passenger travel, had a 50% overall share in 2050. Now that's not infeasible. That requires much better walking and cycling in short distance trips, and buses, light rail, e-bikes dominating medium distance trips. And it requires us to just travel less because, you know, we're living in a more sensible way closer to services. The scenario also assumes that freight transport stays constant to 2030, a slightly smaller floor space per capita, and lower internal temperatures and retrofits to lower residential sector and services sector demand. It requires lowering cement demand and dematerializing the industry, and also the industry taking up maximizing its efficiency uptake. But the benefits it brings are absolutely massive. So the total average cumulative energy system cost falls from 16 billion a year in the E65% to 10 billion a year. It just downscales the whole energy system. It downscales the whole effort that needs to be taken this decade. And that requires far less dramatic scale up in new technologies to 2030. For example, if we're comparing 61 reduction versus 61 with the low energy demand, and this kind of showed this was a scenario which shows the biggest difference. So this shows 4 gigawatts of offshore wind is required rather than 7.5 gigawatts. EVs reach full market share in 2035 rather than 2025. 200,000 retrofits rather than 600,000 in the residential sector, and a 53% increase in electricity demand rather than a doubling of electricity demand. So even though these transformations in the low energy demand scenario, these technology transformations, they're still very, you know, ambitious and hard to reach, but they're far more achievable than these stretch targets. The marginal abatement cost falls. And also, if we look at 2050 in the low energy demand scenario, it requires far less negative emissions technology in the form of bioenergy with carbon capture and storage, and fewer novel technologies to help us to meet net zero. And also this scenario can support many of other sustainable development goals: healthy, sustainable cities, improved well-being, and so on. 4-day work week, wouldn't that be great? So I think what we want to do with this low energy demand scenario is to at least quantitatively show the benefits it brings. In terms of what cost it will bring, we need to do more work with our sort of transport colleagues to understand what it will take to bring about that shift. So it's also really important to remember that it's very likely that one or more of these technology targets will not be met. You know, we're kind of peppering like we need to remove as many fossil fuels as possible, and it's likely that some of these targets will fail to risk the achievement of carbon budgets. Lowering energy demands creates more resilience and brings more benefits. Given if we do require lower energy demands to achieve our targets, it requires a change in approach. So technologies and fuel switches will not be enough. And I think that there's many lessons from how we responded to the COVID-19 pandemic. When we want to collectively tackle a crisis under strong leadership, and the climate change is a real crisis, it requires real strong action. And for the kind of societal response to climate change that we saw very effectively from COVID-19, I think that there's a few things that we need to do which we're not doing at the moment. First of all, the public really needs to understand the gravity of the problem, the science of the threat of greenhouse gases, what's causing the warming, and also what the solutions are. So you still see people saying that, oh, EVs, you know, they still have a higher amount of electricity, or, you know, all bioenergy is unsustainable, or, you know, what about China, you know? So I think we need the kind of strong political leadership and messaging that we had for COVID-19 to sort of explain to people and get people's input into the solution. Second of all, and I suppose I'm saying this from my own perspective as a scientist, but we saw from COVID-19 that the science policy interface was extremely strong, that NEFID advised, the government took decisions, And we know that trust in institutions, trust in science, and transparency in decision-making are key to get the public on board. In Ireland, we had one of the highest uptakes of vaccines because of our trust in institutions. And I think that, and we want to be part of this by being very transparent and open about our modelling as well. And thirdly, people won't come together to act on climate change if there's a perception that solutions are not fair. We have to consider who pays. If there's a perception, even if it's, even if it's not true, that one sector is not doing its fair share, then why should I, go about this big effort and change my life if them over there are not doing it? So we have to make sure that every kind of sector is doing its bit, to bring everybody along. So I think I've covered all these conclusions already, but basically the scale of change required is unprecedented and action needs to be dramatically scaled up. Very high marginal abatement costs. Energy service demands need to meet the 2030 target. The key kind of pinch points there are low carbon electricity, bioenergy, and lower energy service demands. And I think that with these integrated whole systems approaches, we can be a very important part of the conversation. But we also want to be very humble and say that we need multi-model analysis, we need stakeholder engagement, sensitivity analysis, and so on. There's many uncertainties. I'm sure we're wrong in many ways, and we want to work and improve on that as well. So I saw that. I thought I'd find it hard to fill 45 minutes, but I could go on for hours. So that's where I am.